A fantastic pleasure to be back here in Santa Barbara. My first visit since the pandemic, one of my favorite places on the planet. The weather notwithstanding, it reminds me of home. It's great. Anyway, I've been following the developments with this Muon Collider story over the past year and a half, 2 years with tremendous interest. I'm very far from an expert in the most critical question of if Muon colliders are actually possible. And that's, I think, the goal of this workshop has been not to give a definitive answer to that question, but to decide whether it's totally insane or not, and whether there's any obvious showstoppers. And as far as I can tell, the consensus, and we had a really terrific discussion earlier today with the red team and blue team, not fighting as much as I hoped they would, but anyway. You know, you could debate about strategy and this, that, but there's no obvious showstoppers to this idea. I'm here as a fan, not as an expert. We have a number of the experts here, so if, it'll be great to have discussions. We can ask them. But if it is possible, and it seems like, again, there's no showstoppers, it does represent a ridiculously exciting future for high-energy physics. And this is, I think, most evident when you talk to people in their 20s and 30s. I have not seen this level of excitement and enthusiasm in a decade for what could represent a future for the field. So I'll be dead before the Muon Collider turns on. Well, actually, I'm starting to work out a little more, you know. Maybe I have a newfound purpose in life. Anyway, what I'm going to do is describe the motivations first for next big accelerators, period, in general, and then talk a little bit about what's so great about Muon colliders in particular, and then talk about some of the technical and technological challenges that'll take to make this work. All right, so let's just begin with a few things, though. So muons. Okay, so a muon, plus or minus muon, the mass is around 105 MeV, around 200 times the mass of the electron. It's a heavy cousin of the electron. As you all know, the muon decays to an electron by virtual W, muon neutrino, an electron, and an anti-electron neutrino. And the lifetime of the muon is about a millionth of a second. Okay, so 2.2 microseconds. Okay, these are very, very familiar particles. There's around 200 muons per meter squared per second passing through this room right now. Okay, so they're produced by cosmic rays hitting matter in the atmosphere. Now, they decay in the millionth of a second in your hand, so what do you do with them if you're a particle physicist? You say, I know, I take this thing that decays in the millionth of a second and I'm going to very, very quickly accelerate it to very, very close to the speed of light. Okay, so it lives long enough so that I can collide the hell out of them. Right? So that's the idea of the Muon collider. So we have muons and anti-muons. And the center of mass energies that are being talked about are, and we'll talk about why these energies are important from the point of view of fundamental physics, are numbers that people bandy about are 3 or 10 or 30 TeV. Okay? And remember, the energies of the proton beams, the center mass energy at the Large Hadron Collider is 14 TeV, but for reasons we'll review again in a second, that kind of is giving us access to probing physics at the roughly TeV scale. Okay, so because the proton's a messy, complicated object, it's not an elementary particle. The muon is an elementary particle, so this energy is sort of fully available for the high energy collisions. Okay, so this is the velocity that's nicely 0.999, 10 nines times the speed of light. Okay. Now, again, just a few basic things. So people have been talking, for example, over the past decade, in thinking about going beyond the Large Hadron Collider, of For instance, a proton-proton collider that would go beyond the LHC at around 100 TeV. So again, this would probe roughly the 10 TeV scale. If the LHC at 14 TeV is probing roughly the 1 TeV scale. And we can probe the same 10 TeV scale with a muon collider that's 10 times smaller, roughly. So it's around 10 kilometers big. And what's the basic reason for this? Well, it's just the famous fact about synchrotron radiation. Okay, so that's what we're taking these muons, we're taking around a circle of radius r. The power goes like alpha divided by r squared times the energy divided by the mass of the particle to the fourth. So there's this famous gamma to the fourth in the synchrotron radiation formula. And so it scales like the fourth power of the mass. Okay, so 200 times heavier than the electron, that's a factor of 20 billion less loss of energy in synchrotron radiation relative to doing the same thing with E plus E minus collisions. On the other hand, it's not so heavy, it's heavier than the electron, it's lighter than the proton, you can still accelerate it quite effectively. So it's in this very nice intermediate place between electrons and protons. You can accelerate it, but it doesn't lose that much energy. Okay, a few other parameters. So people talk about luminosities for accelerators. And the kind of luminosity that you need is somewhere between 10 to the 34 or 10 to the 35 per centimeter squared per second. Now, where do these numbers come from? We're interested in probing physics at roughly 10 to the minus 17 centimeters is what we're probing with the LHC. So 10 to the minus 17 centimeters, 1,000 times smaller than the nucleus of the atom, around 10 times smaller than the weak scale, the Compton wavelength of the W and the Z particles. For physics reasons we'll talk about, it's really important to take another factor of 10 up from there. So we're interested in cross-sections, the kind of, very roughly, the kind of cross-sections that we're interested in are 1 over the length scale squared. So the geometric cross-section would be somewhere between 10 to the minus 17 and 10 to the minus 18 centimeters squared. So it's 10 to the minus 34 centimeters squared, 10 to the minus 36 centimeters squared. Those are the kind of cross-sections that we're interested in. That's where these numbers come from. The 10 to the plus 34 to 35 per centimeter squared per second is designed for these processes to take place on a human timescale. 1 a second, 1 a minute. Okay, so that over the course of a year, now we're interested in cross-sections that might vary over 4 or 5 orders of magnitude, but we might want to produce 1,000 things, 1,000,000 things, okay? That's where this target luminosity comes from. It's essentially set by the length scale that we're looking for, and the desire for something to happen on the human time scale, so that we can actually do it. Okay. Okay, so that's some of the zeroth order things about the machine. What's the time scale? Well, this is very uncertain, but the most optimistic number that people talk about is around 25 years from now. Okay? Maybe it's 30 years, maybe it's 35 years. Okay, so let's call that 25 to 35. It is not 50. Okay, and I think this is important, right? 25 to 35 is at least a fraction of a human career, unless, okay, 50 is not. Okay, 50 is really like building cathedrals. Okay, 25 or 35, you know, you're a nothing grad student now, you'll be a big boss then. So, all right. So let's now come back to the more zeroth order questions. Why big accelerators, period? And, you know, at some level, this question doesn't need answering, because large accelerators are simply the only direct probe we have of the short distance frontier, the short distance high energy frontier. You can do a zillion other things indirectly, but there's no substitution for going there if you want to see what's going on at the frontiers. And so we go because we must, and because we can. Okay, so this is not like nothing has happened. It's not like all of a sudden we've reached every limit of every technological frontier. Far, far from it. Okay, so not that far from it, but certainly not physical limitations. So there's absolutely no reason from that point of view that we shouldn't proceed. And of course, time and again, in our storied history, doing this has given us structural, profound clues to the laws of nature, not least playing several critical roles in the development of the standard model of particle physics. All right, but if you're someone in another field listening to this entire spiel and seeing this collider and seeing people thinking about these machines, you might be thinking in the back of your head, these people are on drugs, because isn't particle physics dead? Okay, and I think this is a very important question. All right. I mean, after all, we turned on the LHC, we had this spectacular triumph, we discovered the Higgs particle. That's great. After the discovery of the Higgs, the kind of intellectual structure of the standard model is complete. In principle, we have a theory that can be extrapolated to exponentially higher energies than we have available. There's no internal inconsistency, direct inconsistency in the theory. It could make sense all by itself, not quite to the Planck scale, but pretty high up. And we only saw the Higgs at the LHC. We didn't see anything else. And didn't you theorists tell us for 20 years we're going to see gazillion particles lighting up the LHC like a Christmas tree, supersymmetry, extra dimensions? Nothing, right? Absolutely nothing. And anyway, and that Higgs is that particle that was predicted 50 years ago. Yawn. So boring, right? This is a point of view that some people have, and I don't think it's entirely unreasonable. Okay, it's not obviously 100% trivially wrong, but it is wrong. Okay, and I want to explain why it's wrong. And there's a few aspects of this, but the first one that I want to emphasize is that the Higgs itself is really new physics in a profound sense, in a much more profound sense than had we just discovered a whole tower of sort of random particles. In fact, seeing the Higgs and literally seeing the Higgs and nothing else is a really profound challenge to our understanding of theoretical physics. It's a profound challenge to the reductionist paradigm in many ways of thinking about it. And it's really a huge challenge to a theory. It's such a huge challenge to theory that I think a lot of theorists still haven't absorbed it, don't know what to make of it, and are scratching their heads. But when theorists are confused, it's the time to do more experiments, okay? And we've never seen a particle like the Higgs. I want to explain just, now this could be an entire talk by itself, and I don't want to spend the entire talk on this topic, but I want to say a little bit about it. The Higgs is not random. The Higgs is a special particle. And we've never seen anything like it anywhere else in nature before. And if you run into a phenomenon you've never seen anything like it in nature before, and you produce it, you see it, you get a first zeroth order fuzzy picture for what it's about, you don't then experimentally go and walk away, especially when we're very confused about what it means theoretically. So theorists are confused, experimentalists have a totally obvious program, put the Higgs under the microscope and study it to death. All right, so let me explain just in a few minutes why the Higgs is special. The Higgs is really the simplest possible elementary particle. It has no properties other than mass. It's a spin zero particle. It has no charge, just mass, nothing else. And that very simplicity is what makes it so theoretically perplexing. So, the Higgs is responsible for many things. You all know we say that it's responsible for the masses of elementary particles. So the Higgs, for example, the coupling of the electron to the Higgs is responsible for the mass of the electron. If there was no coupling to the Higgs, the electron would be massless, atoms wouldn't exist, you and I wouldn't be here, it would be an entirely, totally different world. So the mass of the electron is pegged to the mass scale associated with the Higgs and with electroweak symmetry breaking. They're not exactly the same scale, there are dimensionless coupling constants that relate them, but there is an overall mass scale that sets the mass of the electron and the muon and the up and the down quarks and so on. That mass scale is the electroweak scale, the distance scale is 10 to the minus 16 centimeters, 10 to the minus 17 centimeters. Okay, and so questions like why is the electron massive are then transmuted to trying to understand the origin of that scale, which ultimately has to do with the origin of the mass of the Higgs particle itself. You've probably also all seen this picture of something like a Mexican hat potential that's associated with the Higgs field. There's a parameter in this potential, m Higgs squared, Higgs mod squared, and maybe some quartic coupling in the standard model. But this is the one place a scale comes in. It has a minus sign, which is where the Mexican hat picture comes from. But anyway, we'd like to understand what's the origin of the scale. The origin of that scale pegs the mass scales of all the other elementary particles. And a peculiar fact about this is that this scale seems vastly different than other length scales that we know about in nature, such as the Planck scale, which is 16 orders of magnitude higher than the energy scale associated with the Higgs. So a very simple question about the world is why there are big objects in it, like you and me and planets and so on. And these objects are big because of a competition between electrical forces that are the pressure holding us up and gravitational forces that want to crush us. And if you equate those two pressures, you get an estimate for the size of the Earth, for example. And the size of the Earth is bigger than an atom by exactly the amount that gravity is weak compared to the electric force, the square root of that ratio. Okay, we have macroscopic objects in the world because ultimately the elementary particles are light. So why does the world have big objects in it is the same as the question, why is this mass scale not up with the Planck scale? Now for other particles, we have a very good answer to this question. For example, why don't we, so this is a mystery for the Higgs, but why isn't it a mystery for the photon? The photon is massless. Okay, the photon is massless. And you might wonder why the photon is going through the vacuum. It can have all these interactions with other virtual particles in the vacuum. Why don't these things give the photon inertia? Why don't they give it mass? Why does the photon stay massless? And there's a very good reason why the photon stays massless, which is that 2 is not equal to 3. Okay? It's a deep fact that there's a discontinuous difference between the number of degrees of freedom of a massless particle with spin and a massive particle. A massless particle with spin only has 2 polarizations. A massive particle with spin has 3, and that's because no matter how it's spinning, you can always catch up with it and then tilt your head and see it spinning in all possible directions. You can't catch up with it when it's massless. Okay, so this is a fascinating discontinuous difference between massless and massive. And that's why the photon is robustly massless, because 2 is not equal to 3. No possible interactions with all this stuff can all of a sudden generate out of nowhere an extra degree of freedom. The same thing is true for fermions. Okay? In all of these cases, and this is also why our friends in condensed matter physics can actually engineer beautiful condensed matter systems that have, as their long-distance excitations, things that look like many of the ingredients in the standard model. Okay, things like gauge fields emerge. Things like chiral fermions emerge. And you can make them emerge in beautiful condensed matter systems. Why can you make them emerge? Because somehow you have to sort of find the right base of attraction of the material that does it, but once you do, it's robust because of this 2 not equal to 3 business. Okay? The same thing for gravitons. So why is the Higgs special? The Higgs is special because 1 equals 1, unfortunately. Okay? Okay, the Higgs only is a spin 0 particle. There's no difference in the degrees of freedom between a massive and a massless spin 0 particle. And there's absolutely no reason why these sort of violent quantum mechanical fluctuations in the vacuum don't give the Higgs an enormous inertia. Now, there's no inconsistency, and by the way, this is also why in the standard model we can't calculate this parameter. That mh squared is a parameter we have to take from experiment. Okay? So we don't have an explanation for why it has the wrong sign. The analogous phenomenon in superconductivity, where there was a Landau-Ginzburg description of the physics, ultimately found very quickly after Landau-Ginzburg a microscopic description in the BCS theory. And we're lacking the analog of that description today. Okay, and that's also why you don't encounter something like the Higgs in garden variety condensed matter systems, even though, while you can make chiral fermions and gauge fields and so on. Okay, so there is something special about the Higgs. We've never seen anything like it elsewhere in physics in other states of nature. And to a theorist, this fact shows up in another way, which is if you try to find a theory where you can calculate the mass squared of the Higgs, where it's not just a parameter, so it's some extension of the standard model, where it becomes calculable, in every such extension that we've ever run into, once you make it calculable, when you make the Higgs down at the scale where we see it, there should have been a lot of other particles coming along for the ride. And that's why people expected it. They were not all on drugs. That's why people expected that there would be a whole bunch of new particles. We should not have a lonely Higgs and nothing else at the LHC. So the fact that that has not happened is very surprising. We've never seen anything like it anywhere else in physics. Everywhere else, we've seen this kind of phenomenon. The logic that I'm talking about here has been borne out. Now we see it in the vacuum of our universe, the simplest possible place. It's different. Okay? So nature has different ideas for what the Higgs is about than theorists do. And as I said, theorists are confused, but what experimentalists should do if you've never seen a point-like spin-zero particle is put it under a microscope and study it to death. And what does that amount to? So you literally want to look at it. Looking at it means looking at the interactions of the Higgs, first of all, with external probes. Okay? But actually, maybe I'll give you an idea. So all of the drama has to do with whether the Higgs looks point-like or not. Okay? Now, if we go down from the scale of the weak scale down to nuclear physics, we have pions. Okay? Pions are spin-zero particles. And pions, ultimately, we understand are bound states. But there is a sort of gap between the mass of the pion and where the rest of the states of the strong interactions come in. So, there is some sort of constant wavelength scale associated with the pion. It's about 1 over 135 MeV. And there's sort of the actual size of the pion. That's around 1 over 770 MeV. That's the mass of the rho meson. Okay? So in the end, the pion is not point-like. There is none of this huge drama associated with its existence. But there's a sort of gap of let's say, about a factor of 5 between its constant wavelength and its actual size. What do we know about the Higgs from the LHC? We know now, and we will basically know, by the time we're done running the whole thing, essentially the analog of this picture is scaled up. Okay? Essentially, it's 125 and not 135, but it's basically the same thing with the Higgs. So there's the constant wavelength size, which is 1 over 125 GeV. And there's the kind of compositeness limits that we can put on it. That'll be roughly, let's call it 1 over 1,000 GeV. Okay? So in other words, we will know it's somewhat point-like, but we could run everything through with the LHC and not know whether it's more or less point-like than the pion. That's bad. We really need to sort of decide whether it's way more point-like than anything we've seen before or not. If we probe the Higgs and we discover it a substructure at right around this scale, that's very interesting. That's kind of, it might lead you down one path, a kind of a repetition of history, peeling back another layer of the onion, et cetera, et cetera. But gone would be all of this drama associated with the challenge to reductionism and all the other things that we talked about. On the other hand, if you go another factor of 10 and it still looks point-like, then we for sure know experimentally that we're in entirely uncharted territory, that we've never seen anything like it before. So there's a target here, which is to understand how point-like the Higgs looks, kind of a factor of 10 better than the resolution we get from the LHC. And it's not a random target. It's not like we all basically already know what it's like. We're just putting in a few more decimal places. It's right already at a sort of juncture where we don't know what to make of it. Okay, so we might see something or we might not, and either answer has some consequence for the way we think about fundamental physics. So how do you do that? Well, first you look at whether the Higgs looks point-like to external probes. So the most obvious thing you could do is to see how the Higgs couples to photons, sort of almost literally look at it, or to see how the Higgs decays to a pair of photons, which is what the Higgs actually does. Or other external probes, Z's, for example, or quarks. Okay? And so you'd like to do this, essentially the resolution 10 to 100 times better than what we get from the LHC in order to sort of settle which side of this divide we're on. Something else that you'd like to do is to see whether the Higgs looks point-like to itself. Okay, so that's one more order. And to do that, we have to see how the Higgs couples to itself. Okay, that's something that we're, from the LHC, maybe going to get some evidence for whether this interaction even exists or not. But we're not going to know whether it's there of the size that would be consistent with a point like Higgs. We'd like to be able to decide that. Ideally sort of measure this to a few percent or something to really know whether it's there, whether the Higgs looks point-like to itself. And we'd also like to know whether the Higgs couples to anything else for obvious reasons. Okay? So we'd like to see, we know how the Higgs decays to standard model states, but does the Higgs decay to other things that are invisible to us? Okay? So, and you would ideally like to know that by sort of measuring the total lifetime, the total width of the Higgs, and comparing it with what we expect. Another important thing is that I didn't explain it, but those quantum mechanical fluctuations in the vacuum that I was talking about get, just by dimensional analysis, stronger and stronger, like the square of the energy scale that you're probing. So if you just go up to an energy scale E, you're going to probe these vacuum quantum fluctuations by an amount E squared. Okay, so if you go up by a factor of 10, then you're in territory where you're probing whatever's going on with these vacuum fluctuations a factor of 100 more powerfully than you were before. All right, so these are things, all three of these things are facts about the Higgs we need to know. That we need to know they have zeroth order consequences on our thinking about fundamental physics, and we're not going to know them from the LHC. So that alone is what you might think of as sort of guaranteed things that we could learn by building an accelerator that goes beyond the LHC. What about things beyond the Higgs? Well, here, I should say up front, there's absolutely no guarantee that there are particles beyond the Higgs. As I said in the beginning, the theory is consistent, can be extrapolated to exponentially higher energies. All right? But dark matter could be some purely gravitationally coupled particle that will never produce at an accelerator. I mean, these are all possibilities. Okay, so there's no guarantee. I should say that this idea of guarantees is sort of ridiculous. There's almost never been a guarantee. And the LHC was an exceptional situation where we knew ahead of time that some phenomenon had to happen at around the electroweak scale, something like the Higgs. Before that, no guarantees. After that, no guarantees. This is the normal situation where there are no guarantees. But, sorry? Okay, yes. Okay. But I do want to stress the following point, which is that it's also not true that there's no reason to expect new particles just 10 times heavier than the reach at the LHC. There are good reasons, there are lots of good reasons, no guarantees, but there are lots of good reasons why we might have particles that were missed at the LHC, not because we got unlucky or we're moving the goalposts after we didn't see them, they're just not there. We knew ahead of time they couldn't be produced at the LHC. But they will be produced at colliders with 10 times higher than the LHC energy and not 100 or 1,000 or 10 to the 10. Okay, so that's a good example of this is dark matter. Okay, so probably most people, and maybe the cosmologists or astronomers in the audience, everyone's heard of WIMP dark matter, and maybe also has a sense that somehow WIMP dark matter is dead. Okay, if not dead, it's on life support, and that's why people are looking at every other conceivable kind of dark matter, 90 orders of magnitude parameter space. We're going to spend 1,000 years looking for dark matter. Okay, this is false, just dead false. Okay, the very, very simplest models of WIMP dark matter that you could have written down in the year 1980, they probably were written down in the year 1980, do not give you particles that are accessible to the LHC. In fact, the very dumbest theories of WIMP dark matter, where the W in WIMP literally stands for the weak interactions. And so we can really do a responsible calculation for what the relic abundance would be. It would be like an electroweak doublet particle or an electroweak triplet particle. They arise in zillions of theories, but we don't even need to talk about the models. You can calculate ahead of time what mass they have to have. You could have calculated in 1980. And the answer is 1 TeV if it's a doublet, 3 TeV if it's a triplet. These particles will not be seen at the LHC. They're just too heavy to be produced at the LHC, A. B, for reasons that have nothing to do with the mouths of the theorists, they have minuscule direct detection interaction cross-sections. Okay? Right around the famous neutrino floor of the direct detection experiments, around 10 to the minus 47. Okay, so maybe they'll be seen at the very, very end of these runs. Certainly there's a good reason why they've not been seen so far. And these are not the complicated or Baroque models. They're the simplest models are the ones that are alive now. The LHC null results and the direct detection null results have ruled out the Baroque models of WIMP dark matter. They have not ruled out the simplest models of WIMP dark matter. We knew that in 1980. Well, we didn't know they're not going to see them, but anyway. But the mass scale was set. Not a matter of moving the goalpost after we haven't seen anything at the LHC. What you need for that is a collider with the reach of particles 10 times heavier than the LHC. Okay? And then you can actually produce the dark matter particles directly. Beyond dark matter, there are scenarios for physics beyond the standard model. Some of my personal favorite pictures for what's going on beyond the standard model. Again, pictures that were there and were my favorite pictures well before the LHC involved not seeing all the particles at the LHC, for sure. Okay? But in many cases, 10 times higher than the LHC would see at least part of the spectrum. For example, strange versions of supersymmetry that were my own favorite ideas, but there are a number of others as well. A broad point I'd make is if you're far from the field, even close to the field, you might have an idea that this is the story of the past decade, that theorists knew for sure Susie, 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 and then whamp, the LHC bunks us all over the head, and it's wrong. Now we're fucked. Okay, so now, okay, and it's not like that. Anyone looking seriously at the data in the early 2000s, late 90s, early 2000s, knew there was something a little bit wrong with that picture. The thing that's been bumped over the head are the ideas that were popular in the 1980s and the 1990s. And many of those ideas were already in trouble in the early 2000s. I remember going around to like talks with people happily showing supersymmetric spectra with particles that are actually still alive today at the LHC. Okay? And that's what they're already forced to from models back then. There was something wrong already back then. All right? And that's why many people started thinking about variance in the 2000s. And some of those theories are alive, and some of them have gained support from the LHC data, even. So it's not the case that they're all, only now that we didn't see anything, we changed our tune, and now it's, oh, just give us another factor of 10, right? That this is, there are scenarios for what's been going on that people have thought about. They're not obscure. There are thousands of papers on them that have been actively thought about, where we would see the particles 10 times higher energies with a good reason for having missed them at the LHC. I'm just saying that a lot of the discussion about future accelerators is about how awesome the Higgs is, but it's not, there are reasons to expect, no guarantees, but reasons to expect that we might see new particles also. All right, so now with largely these motivations, people have been talking about a great program. I think it's a very it's an exciting program where you build Higgs factories with E plus E minus collisions. Maybe to start with, E plus E minus collisions at pretty low energies, around 240 GeV, where the Higgs production cross-section is maximized. You can sort of produce the Higgs through this simple process with an E plus and E minus annihilates to a Z particle and kind of emits a Higgs and a Z. All right? So the center of mass energy around 240 GeV. And then you can go to maybe higher if you want. And also proton-proton colliders at 100 TeV. Okay? This would produce millions of Higgs particles and would tell us answer conclusively this question that we talked about. To measure the coupling of the Higgs to external probes, a factor of 10 to 100 better than the LHC. This would produce billions of Higgses in the sort of messy environment of a hadron collider, but would tell us about the existence of this 3-point, the Higgs self-interaction. and measure it to the few percent level, it would almost cover the, pressing a little bit, all of the room that we talked about for the simplest models of WIMP dark matter. Again, goes to higher energies, of course, so it probes the vacuum fluctuations by a factor of E squared more. All right, so the story that I've talked about, and of course there's a scenario where you build a 100-kilometer circular tunnel, and you do this first, and you do this next in that 100-kilometer tunnel. Okay. What's exciting about the Muon collider is that it can do both of these things at once. Okay? E plus E minus colliders are famously good for precision because the electron is a point-like particle. Proton-proton colliders are good for the energy frontier. But not so much for precision. Why? Because, well, the proton is this big messy bag with quarks and gluons on the inside. And first of all, the center of mass energy of the collision doesn't all go into the individual quarks and gluons that are banging into each other. There's sort of a picture where you imagine that there's some fraction of the momentum of the proton is carried by quarks, antiquarks, gluons. And even if you start with what you think is a quark, it could radiate a gluon, and which would turn into another couple of quarks, or they could radiate a gluon and turn into another couple of gluons, and so on. So depending on the energy scale of the process, the sort of content of the proton changes. So we don't have an ab initio understanding directly from first principle calculations for what these numbers are. We have to ultimately take them from experiment, which is one of the sources of messiness. This messiness is also very good, by the way. So it is bad that it degrades the sort of overall energy, so that, again, roughly we have 14 TeV collisions, but we're probing the TeV scale. So there's a rough loss of overall factor of 10 in the actual scale that you're probing. But it means that you have a rich initial state. Okay? It's not just, you have these sort of all sorts of different things that you can pull out of the proton and have them bang into each other. So there's lots of different kinds of physics that you could probe with exactly the same collisions with the same protons over and over again. Okay? But as I said, what's exciting about the Muon collider, if it can work, is that it's 2-in-1. Okay? We can get both the precision of an E plus E minus collider, because the muon is also a point-like object, but also very beautifully, we get a very rich initial state. And I want to explain this point, because this is one of the sort of coolest basic physics points about the Muon collider. Okay, so the first point that you have the same precision of an E plus E minus collider is clear. But let me just say at zeroth order, obviously, if we can go to 10, 20, 30 TeV, we have the energy reach of a proton-proton collider. We're colliding point-like objects, so that's we have a clean environment, high precision. People talk about making 10 million Higgses at a Muon collider. Okay, 10 to the 10 million clean Higgses. So the Muon collider is clean. So you might think you have a process like this: mu plus mu minus annihilates to something, maybe produces two particles. And so the reach for this process, the reach for the mass of this guy is basically the center of mass energy divided by 2. Okay, just to pair produce them. On the other hand, if you think very naively, all of these cross sections by dimensional analysis go like 1 over energy squared. So you would think that that's also very bad, right? If you go to higher energies, all these cross sections are getting tinier and tinier. Okay, so it's very clean, but the cross sections are getting tinier and tinier at the same time. And this is the thing which is false for an interesting reason. Okay? The initial state in the Muon collider is rich. It's kind of not quite as, but getting to be comparably rich to the initial state in a proton-proton collider. You should still think of it as kind of a messy set of things hitting each other, except now the mess is completely calculable. Okay. And what is the physics? The physics is continuously connected to classical radiation. Okay? So, if you have any charged particles, muons or no, coming in and you have a picture like this, then there's a lot of acceleration here in the middle, and you know what happens. You have you produce electromagnetic radiation, and the radiation is sort of beamed in the directions of the initial state and of the final state. Okay, so we have this kind of another direction goes like that. Okay, so that's the basic physics of radiation. Just acceleration, right? So there's the Coulomb field of this guy that isn't there anymore, which is why it has to be carried off by the radiation in that direction, and similarly for all the other lines. Now, how do we understand this in quantum field theory? Well, we draw the picture. There's some sort of collision here, but we draw a picture where we attach photons to all these lines. And classically, that's everything there is. In the full quantum mechanical theory, there's more. For example, we can have these things convert to electrons and positrons if we just have QED. If we have non-abelian gauge interactions, they could split into extra gauge fields and so on. All right? But this is basically the physics of radiation. Radiation produced by very hard collision, large acceleration. Now, if you're a very naive, dumb Feynman diagram person, you would think, gosh, how do you possibly produce lots of radiation? Right? I mean, radiation is like zillions of photons. Where are these zillions of photons coming from? Don't I have a factor of alpha, 1 over 137, every time I emit one of these guys? Why do I get lots of photons? And the answer is that there is an alpha, but the figure of merit for the radiation that you emit is actually enhanced relative to alpha by 2 logarithms. There's a logarithm roughly of the energy divided by a much lower energy scale that cuts off the soft momenta, and another logarithm that cuts off momenta that are sort of collinear to the direction of the particle. Okay? So there are these. So the real figure of merit for the rate of emitting these things is not set by alpha, but by alpha log squared, roughly alpha log squared of energy divided by some scale. A very big headache in the strong interactions is we don't know exactly what to put in for this scale. Okay? And so there's a lot of, and this goes into how we think about the phenomenon of producing jets at hadron colliders and so on. There's the analog of this process just with color radiation. And again, as we said, just the sort of initial content of how much of different quarks, antiquarks, gluons is also something that has to do with the strong coupling physics of the strong interaction that we can't predict ab initio. But here, for electroweak charged particles, everything is completely calculable. All right? This is the figure of merit. And if you put alpha weak here, you put MW here, that number is of order 1 for E of order 10 TeV. That's really fascinating that starting at around 10 TeV, the collisions of muons are effectively making classical electroweak radiation. Right? And we're seeing for the first time the standard model look like electroweak symmetry is actually restored. Radiate W's and Z's the same way it radiates photons and everything else. Right? Now, as I said, the physics that we're talking about is continuously connected to this classical radiation. But even at somewhat lower energies, it means that we should think about the muon, and we should think about the collisions not just as the muon, but the muon of this whole cloud of electroweak vector particles participating in the collision. Even some quarks and gluons, too, as these splitting processes continue. So this is another slogan, is that you should really think of the muon collider is a vector boson collider, or an electroweak vector boson collider, in much the same way that the LHC is actually a gluon collider. Okay? And this means that if we come back to what we're talking about, it's still true that if you want to produce heavy particles, this doesn't change, That cross-section is there, it's small, but you're looking for something new and heavy, so that's fine. You're happy to pay a price to produce something new and heavy. But at the same time, if you want to make Higgses, you don't have to sort of directly do this. Instead, the muon comes along and emits a W. The other muon emits a W. The W's fuse and produce a Higgs. And these W's can have much smaller momentum. In fact, precisely when they have much smaller momentum and energy is when this effect that we're talking about is enhanced. It's exactly the sort of soft radiation that's coming in the, along with the muons. And so the effective center of mass energy associated with these collisions is not that of the machine, but that of the soft particles, and therefore is large. And this is, in fact, the process that dominates the cross-section for producing the Higgses. That's why I can go to incredibly high energies, and at the same time make 10 million Higgses in a clean environment and study them to death. All right, so that's a sense in which it's two machines in one. Can I have 5 more minutes? Okay. That's a sense in which it's two machines in one. Now, there's some very interesting complementarities. For instance, with just measuring the properties of the Higgs. So, you know, obviously all these studies have got to be done more accurately and so on, but the sort of, at 0th order, this sort of factor 10 to 100 improvement on what we know about the way the Higgs couples to other particles relative to the LHC we can also get from the muon collider. Muon collider can also see the two Higgses merging, probe the self-interaction of the Higgs again to the same few percent level accuracy. There are some interesting differences. There's a very, very important, of all the sort of indirect, of all the couplings that, of how external things couple to the Higgs, the one with two Z's in the Higgs is an especially important one. And this is something that the conventional, that the E plus E minus Higgs factories will nail to about 0.1%. Whereas the muon collider will get it to about the percent level. Okay, so this is something which is better at an E plus E minus Higgs factory compared to a muon collider. On the other hand, there's a very cool thing that you can do with a muon collider, which is get a direct measurement of the width of the Higgs. And you can do that because the muon is heavy, so it has a larger coupling to the Higgs than the electron does, much larger coupling, 200 times bigger coupling. So the actual production, the cross-section for producing the Higgs just on resonance is not that small. Okay, so you can make 10,000 Higgses if you tune the energy of the machine and you have good resolution on the energy. And so you can do a scan. Okay, you can just scan the center of mass energy and just see the curve go up and down, see the Bright-Wigner shape, and measure the width of the Higgs directly. And that'll give you a measure of the width, a direct measurement of the width of the Higgs to the sort of percent level, and tell you again whether there's anything else out there that the Higgs is decaying to or not, but in a direct way. And that's something that's difficult, more difficult for other machines. So that's a nice complementarity. Again, the energy reach means if we have a 10 TeV, 20 TeV muon collider, it easily covers the possible existence of the simplest models of WIMP dark matter, the same quadratic reach of virtual quantum fluctuations associated with the Higgs. All those things are exactly the same. And as I said, there's this qualitative, beautiful fact that we finally see the standard model work in its unbroken phase. Okay, see what it really looks like when the electroweak symmetry is entirely restored. There are many other things. And of course, many other things that people are exploring. There are synergies with other fields. For example, obvious synergies with neutrino physics, because you make these muons, and muons are decaying to neutrinos, so making a muon beam is giving you a neutrino beam at the same time. And what do you do with these incredibly high energy neutrino beams? I don't know, but there's other people know. But this is definitely something other people care about. Okay, so it's okay. So. Maybe I can just take, unfortunately, just 5 minutes to tell you something about the challenges. And maybe this is okay, because I'm really not an expert on the challenges, but I can at least tell you about some of the things that I've been learning. So So what are the challenges? Well, first, how do you make these muons? So you have a beam of protons at 8 GeV. You lay it into some graphite, make a ton of pions. The pions decay to muons. So you get a beam of fairly low energy muons, 200 MeV muons. People tell me it's about that big, okay, just in space. Okay, so you have sort of 10 to the 12 muons in something about that size. Okay, the spread of momenta, they're coming out around half the speed of light. The spread of momenta is 50 MeV or so, overall 200 MeV or so. All right, now, you have to take this thing, and in order to get to those luminosities that we're talking about, you've got to squeeze them a lot, okay? So there's a 6-dimensional phase space, x, y, z, momentum x, momentum y, momentum z. The overall volume in phase space that you have to shrink is about a factor of 1,000,000, okay? So you got to take this thing that's about that big with 30, 40, 50 MeV spread in the muon energies and collimate it to something that's about 1 millimeter big with a spread of energies of maybe 2 MeV. All right? So that's what you have to do in order to make the whole thing worth it. Okay, now, because of Liouville's theorem, you can't, by any conservative process, change the volume in phase space. So it's not a matter of steering, doing this, turning on an electric field, doing something with a magnet. Anything you do will just bloop, 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 move it around, but not change the volume. So that's why the word cooling comes in. You have to cool it. There has to be something non-conservative. And so what people are talking about is taking this ball and passing it first, focusing it with some very strong magnets, and passing it through a material so it can lose energy. Okay, so the material is lithium hydride. I hate chemistry. I know nothing about any of these things. This is just words to me. Okay, lithium hydride. All right. Maybe there's other materials. The idea is to have something which is which just allows the muons to scatter and lose energy, but not scatter so much that that it randomizes again and thermalizes the whole process. Okay, so you do that, and what happens is the whole thing just slows down a little bit after you put it through a pass. Then what you do is you then accelerate it again in the direction you want it to go. Okay, so everything loses energy in both the longitudinal direction and the transverse direction, but then you gain the energy back in the direction you want it to go in the transverse direction. The net effect is that you've cooled it in the transverse direction. Okay? And then you just do it again and again and again and again. So you got to get to the factor of 1,000,000. And, when I was a kid, in graduate school, people talked about muon colliders, and all the senior people have told me it'll never work, cooling, kill it. You can't possibly cool. Up to, I don't know, as long as I can remember, until recently, it was always, cooling's impossible, cooling's impossible, cooling's impossible. Apparently that's just false. Cooling is not impossible. It has not been demonstrated. The whole 10 to the 6 has not been demonstrated. But what has been demonstrated in the past couple of years is a sort of first pass to go through this stuff that gets you a factor not of 10 to the minus 6, but of 0.9. Okay? However, it's 0.9. This is my understanding. Maybe the experts can correct me if I'm wrong, but this is a 0.9 that there's no reason you can't imagine doing again and again and again and again. 0.9 to the 120 is 10 to the minus 6. Okay? And that's what people are talking about. People are talking about doing this in a straight line of about 1 kilometer, passing it through this whole array of things to get you this collimated muon beam. Now what you have to do is take this thing and accelerate it to your 0.9999 10^9 the speed of light, all before a microsecond when the muon decays. Okay? So it's fucking amazing. Okay? Completely amazing. And to me, very, 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 very exciting. There are other problems, but Lars is going to kill me. That's maybe all for the good. Another thing that people used to talk about a lot is neutrino radiation. Okay, so the muons are going around, but in all colliders there are straight sections, and the muons are decaying. They're neutrinos, very high energy neutrinos. The cross sections for the neutrinos grows linearly with energy. The collimation is getting smaller with energy, right? So in these unfortunate directions that you just keep passing over and over and over again, you're just dumping a lot of neutrinos in that one direction. And of course, they will interact with material at these incredibly high energies and give you some non-negligible fraction of radiation. Okay, so that's something that people are worried about because, you know, you don't want, in the panel discussion today, someone was worried about the poor bunnies that are getting radiated by all these neutrinos. And that's their ideas about that. Their idea is to wiggle the beam a little bit so that you don't keep hitting the same spot over and over again. Or another idea I heard is to tilt the machine a little bit so that the straight sections either go deeper into the ground or go up into the sky, where maybe some crows are harmed every now and then. No, that doesn't happen. Okay. So, another challenge is that the muons are constantly decaying, and so there's something called beam-induced background. That there's all the stuff in the decay products aren't disappearing; they're smacking into all of the material surrounding the beam. What do you do about that? So there's there are some ways in which that's a problem. There's some ways in which it might be an opportunity. Anyway, those are the challenges. And again, I'm not an expert, and I hope people will ask the experts as I imminently end. But I want to say that the main zeroth order question about this entire enterprise is it insane? And the answer is no. It is not insane. There are, as I said at the beginning, there's the whole discussion, at least that I saw, there's criticism, there's skepticism, but not about sort of obvious, crazy showstoppers. And I think it's incredibly exciting. I think it's incredibly exciting because it's something completely new. We've never done anything like it before. And it's exciting in a way that's easy to explain to professionals, and it's easy to explain to lay people. Right? You tell people we're going to build another collider, if they care at all, they're like, oh, those are those big things, and they're like, yeah, so what are you doing? Well, we're just building a bigger one. Okay, it's great. It's terrific. But if you tell them, look, there's something that in your hand decays into millions of a second, but we accelerate it to 0.9999, 10 times the speed of light, and it's 10 times smaller than it was before. It's obviously new. It's obviously different, and it's obviously cool. Okay. And so I think it's very important to have something whose excitement is appreciated both by professionals and by normal people. And I think this definitely has that flavor. The final thing I'll say is that if we're going to do something like this, the time to start thinking about doing it seriously is definitely now. And it's definitely now for a whole variety of reasons, not least of which is that we have luckily still the following situation where there is a confluence of existing expertise to do it, not trivial, but also enthusiasm from young people who are willing to spend 2 or 3 decades of their life doing it. Those things exist now. I doubt they'll exist 10 years from now. Okay, so if we're going to do it, we have to fish or cut bait and decide if we're going to do this kind of wonderful, crazy thing with our intellectual lives. All right, thank you very much.
Thank you, Nima. Questions from non-Muon Collider participants? Any cosmologists have a question? Dick, hang on.
So, of course, I'm as intrigued as anything by the neutrino quote-unquote backgrounds that are going to be raised here. Within the context of something as mundane as a right-handed neutrino, do you see any possibilities for unearthing something like that?
Sure.
Oh, well, yeah, that's not much of an answer.
No. I only focused on talking about things like there are the properties of the Higgs studying to death are the guaranteed things that we'll learn. Things about dark matter is not guaranteed, but I brought it up simply because it's so canonical. I mean, people talked about it for a long time. There's no reason that the simplest things are still alive, so we might as well decide one way or the other whether they're alive. I could give, and the people actively working on this could give you several hours of talks on all the other things that might be out there that we would have access to. So certainly, if they're right-handed neutrinos somewhere in the neighborhood of the 1 to 10 TeV scale, at reasonable couplings, of course, we will have access to them. But but anyway, that's a different kind of talk. But if you're interested, there's a zillion people here who will talk your ear off about these things. So.
More questions from anybody? I excluded some. Yeah, Joanne. Right. No, please don't, because we want to get it recorded. Yeah.
I was wondering about, you said there tons of supersymmetric models right at this energy scale? Is that what you?
I didn't say tons, I said my own favorite.
Oh, okay.
Yeah.
Okay, is there a name
Science
for
is
it?
not
I
a
want to look
democracy.
it up.
You just have to be right. Yeah, but no, I mean, but less jokingly, it's been sort of natural and bad word to use in this context. It's been straightforward. Many of the simplest theories that broke supersymmetry did not make the fermions and the scalars have an equal mass. Because it's much easier for the scalars to get a mass, you just have to break supersymmetry, than for the fermions to, which also needs some breaking of chiral symmetries. So many of the simplest models that broke supersymmetry actually had the fermions about 100 to 1,000 times lighter than the scalars. And if you just say, just from data, we need the fermions to be dark matter, that they're down at a few TeV, like they could be in the simplest possible settings, and the scalars would be, up at 100 or 1,000 TeV. They might be lighter. It's possible that there might be stragglers as well, but that's a scenario where the fermionic particles would be seen with 10 times higher energy than the LHC. The scalars would not. And again, this is not something that was made up after the LHC, nor is it especially obscure. I mean, people were studying it very actively before the LHC. So I'm just saying that, anyway, that's my own personal favorite picture of the world. Many other people have their favorite pictures of the world, but many of them were not, I mean, not that there's anything wrong with responding to the data and changing your models, but I want to, there's nothing wrong with that either, but that's part of the way we do science. But it's just to make the point that these were not things that were just sort of made up afterwards. There are pictures of the world that people talked about well before the LHC, where it was sort of, and I do want to stress that the fact that the LHC was perhaps not going to discover supersymmetry was something that anybody who seriously looked at the data in the year 2000 would be talking about, and many people did. Okay? It was not a majority of theorists, but it was a sizable minority of people who were seriously looking at it who thought that this might be going on. It's not a big shock.
Okay, more questions? Yep.
Is there any point about to first think about a muon collider at lower energy? I mean, technologically that would be easier, I think, and you could get some of that. But is there any physics that you might learn? Or
yeah, I mean, there's a lot of discussion about how you do the staging. So you might start at 3 TeV. You might anyway. I think the answer is that all of these questions are premature until we know more about what's feasible. I think this workshop and all the work that people have been doing over this past year have answered the question, is this something that serious people should spend a lot of time on? The answer is yes. And I think once we start spending this time, come back and ask your question in 2 or 3 years and we'll have a more responsible answer. You'll also notice I didn't say anything about costs. This is it's obviously, 10 billion in your favorite units. But maybe not even so obviously. I think that's also irresponsible. Nobody really knows what the cost of these things are. Everything is different. In a hadron collider, everything scales with the size of the machine. Things also scale with the size of the machine, but the machine's a lot smaller. The technology is pushing the limits in many other directions. Lots of new things have got to be developed. That's part of what makes it so exciting. Very hard to multiply all these factors and give a responsible answer. I would not give an answer if I was any of these people. But I would give an answer in 3 or 4 or 5 years when the studies have been done.
Thank you, Nima.